Well, good morning. It's a real pleasure to be here and have this opportunity to talk to you about one of the most amazing stories in innovation in human history. We're going to do this in two parts. I'm going to be giving the first part of this talk, sort of a fun look at the history of microelectronics. The second part will be given by my colleague, Professor Kaushik at Purdue, who will talk about the kind of innovation that is going to be needed to continue to fuel progress in the second half of the Silicon century. So let me begin with this. A few years ago, one of these social media sites ran a contest. And the contest was to say, if someone from the 1950s suddenly appeared today, what would be the most difficult thing to explain to them about life today? I remember the 1950s. A few of you may too. This was the winning answer. I possess a device in my pocket capable of accessing the entirety of information known to humankind. We don't stop and think how amazing these things truly are. The second half of the winning answer was, I use it to look at pictures of cats and to get into arguments with strangers. There's always an upside and downside to technology, but this really is an amazing technology. So what I'd like to do in a few minutes is just talk briefly about how all of this happened, very quickly about where we are today, and then thinking about the way forward. And then I'll turn the second half of the talk over to my colleague, Kaushik. So back up, let's talk about electronic devices, the basic components of all electronic systems. It began with the vacuum tube, and it actually began when Thomas Edison was inventing the electric light bulb and noticed that something was coming off of the filament. A few years later, the physicist J.J. Thomson was able to confirm that what was coming off of the filaments were actually electrons, and he won a Nobel Prize for that. Just a few years later, that concept was turned into a functioning electronic device, a diode, a device that could pass current in one direction but not in the other. And then 1 year later, a metal grid was put between the cathode and the anode, and you could control the flow of electrons, and you could build amplifying and sophisticated electronics. And that really, I would call that an example of opportunity-driven innovation. We suddenly were aware that we could do wireless communication. There were electromagnetic waves, and we began to think about how can we take advantage of this new degree of freedom that we have. And it was really a transformative technology that people don't remember. It ushered in what's called the golden age of radio. We could communicate, we could send entertainment across the nation, across the world. Families gathered around their living rooms to listen to radio shows or fireside chats from the president. And it was really an amazing transformative technology. And when, shortly after World War II, we began to build digital computers, we built them with vacuum tubes. And if you look at this, it has less computing power than the cell phone that I have in my pocket right now. It was powered with vacuum tubes. It consumed a lot of space. It consumed a lot of power. And there was actually a person whose job it was to, every time one of these vacuum tubes burned out, to replace it as quickly as possible so the calculation could continue. So it had some challenges. Now, people realized that there would be, conceptually, there are other electronic devices that could solve some of these challenges. So way back in 1925, Julius Lillenfeld patented a device called a field effect transistor. And those of you that know something about transistors will recognize that there's a source of electrons here. There's a drain where the electrons flow out. There's a channel where the electrons flow from the source to the drain that are controlled by a gate electrode. So this was sort of an obvious way to think about building an electronic device, a solid state analog of a vacuum tube. But the technology just wasn't there to do that. Well, there was a lot of advance in technology during World War II. Semiconductor physics and materials and technology progressed, and Bell Labs decided that it was time to make a concerted effort to see whether semiconductor technology could be put to use. And in 1947, the transistor was invented. This is the 75th anniversary of the invention of the transistor this year, so that's a significant event. So this is an example of challenge-driven opportunity. These vacuum tubes had a lot of problems. They consumed a lot of power, they burned out frequently, they took up a lot of space. People were looking for a better electronic device. This is a replica of the first transistor. I call it more the discovery of the transistor than the invention. They were trying to produce a transistor, the one that Julius Lillenfeld had patented in 1905, and they had a number of problems in doing so. And as they did some experiments to sort out the problems, they discovered another effect, and it was a different kind of transistor. It was a bipolar transistor. If you look at this device, it would be hard to predict the impact that it had in modern society. You know, that thing there looks like a bent paper clip, and there's a couple of terminals, and that's a slab of semiconductor. The first was germanium. So we really come a long ways since that day. Many people will argue that the transistor was the most important invention of the 20th century. There's some interesting history that you can see about it, this PBS show. So very quickly, people began to build transistors, to put them in packages. It had 3 terminals. They weren't called source, drain, gate. As in Lillenfeld's device, there was a different device. They were called emitter, base, collector. But you could begin to put them to use. They weren't particularly good devices. They were fragile. They couldn't consume a lot of power. They didn't work at high frequencies, but people started to look for what use could they be put to that we can't do with vacuum tubes. Well, only a few years later, they were producing portable radios. This is one that was produced in Indianapolis. You can see that it's a little bit big. She's holding it with 2 hands, but this was something that would be very difficult to do, carrying around the large batteries and vacuum tubes. So it ushered in a whole new era of personal entertainment devices. Things really took off in 1957. When I was a kid, I can remember this happening with the 6-transistor shirt pocket radio. This was an even smaller radio that you could put in your shirt pocket. Actually, Sony was a marketing genius. He had specially made shirts for his salesmen that were slightly larger than the regular shirt pocket size, so that his salesmen could go around with it in their shirt pocket. But this is really an example of taking a device that wasn't a replacement for the vacuum tube, that's what they were searching for, but that could do things that couldn't be done by vacuum tubes. So this is an example, I would call it opportunity-driven research. We have this new device, what can we do with it? And these were niche markets at first, but people were really identifying uses to put this new technology for. Well, this is where Silicon Valley started to build transistors of this kind. And that was done in the late 1950s and early 1960s in Silicon Valley. The first major company to do that was Fairchild Semiconductor. There's an amazing history and story about that you can watch as well. So there were a few people that realized that things have changed. Transistors were still serving niche markets. Frederick Turman is, you may or may not know about him. He's famous for 2 things. He had a long-time career at Stanford University. When people talk about the history of Stanford University and how it became so great, they talk much more about Frederick Turman than they do about any Stanford University president. So he had a huge impact there. He's also known as the father of Silicon Valley. Right? And in 1960, he saw where things were going. Mainstream technology was still vacuum tubes, transistors were still a niche market, but he said, hey, the future of electronics is going to be all about transistors. And the other interesting thing that he said is that education is particularly important. This is a sophisticated science-based technology. Education, especially graduate education, was going to be necessary in order to realize the potential of this new technology. About that time, almost exactly the same time, a group of academics and people in industry realized that we don't have any textbooks to teach new engineers this new technology. They're all being taught vacuum tube electronics because all of the textbooks are vacuum tube based. In order to fuel innovation, we're going to need to develop a whole new generation of textbooks and courses. They got together and wrote a set of 6 or 7 low-cost paperback volumes that for the first time allowed instructors to teach semiconductor electronics. And then things really took off. I remember using 1 or 2 of these textbooks when I was an undergrad. And you look back on them, you read them now, and they still read, they're modern. They're the basis of our way of understanding solid-state electronics today. So that had tremendous impact. So another point I'd make is that in fields like this especially, education is a critical fuel for innovation. Okay, now as we're going through this story, another thing happened. And some of you know Isaac Asimov, the science fiction writer. So Asimov said that this was the most important moment since mankind emerged as a life form. Can anyone guess what this is? Come on, it's the most important moment. It's the invention of the planar process. What is the planar process? It is the process invented at Fairchild Semiconductor to manufacture transistors in a more effective and better way. And very quickly, within a year or two, people realized that we don't need to manufacture transistors, cut them apart into pieces, put wires on them, put them in a package, and then wire them up in circuits. We could put all of the transistors on a piece of silicon, wire them up, all on the silicon chip, and that got things started. That was really a significant moment. Gordon Moore was at Fairchild Semiconductor about that time, and he started to notice that every year we put twice as many transistors on a chip. Electronics become twice as powerful. It doesn't cost very much more to put twice as many transistors on a chip. That's now called Moore's Law. He made a plot there and said that this will probably continue for a few years. When I was a junior undergraduate, I think Intel released its first microprocessor chip. It had a little over 2,000 transistors, and Moore dared to extrapolate 10 years where we would get close to 100,000 transistors, right? Well, the amazing thing is that this has continued as long as it has. Basically, more than 50 years, almost 60 years, we've continued to double, not every 12 months, but every 18 months or 2 years for a long, long time. It's only recently begun to slow. We started with the first microprocessor with a couple thousand transistors on the chip. We're now, a sophisticated chip might have 50 or even 100 billion transistors on a chip. And this is just one of the most amazing things that have ever happened. How could we keep this going? I remember a number of times in my career where we hit the end of Moore's Law, and people always found ways to keep it going, time after time. Eventually there's an end, but it hasn't quite happened yet. And you know, around the turn of the century, something happened. The number of transistors and the sophistication of these systems on a chip reached a level where almost anything you could conceive of could be done. And that was really a turning point. So one other point I want to make is that, you know, this is just incremental, step-by-step process, but it was transformative when it was compounded over decades. You just keep making progress and keep advancing the technology year after year, decade after decade, and the impact is transformative. So what happened when we could put 100 million or so transistors on a chip? We could produce devices like this shortly after the turn of the century. They have a lot of technology inside them, but the heart of it all is CMOS transistors on the chip, and complemented by a whole variety of other devices. So where are we today? Electronics is increasingly pervasive. It's in everything. It's in our toasters and our automobiles and everywhere. The demand is exploding, where we have this insatiable appetite for more and more computing and more memory. But things are getting really challenging. We may be nearing the end of Moore's Law. The leading edge chip fabrication facilities are costing about $20 billion now. There are only 3 companies in the world that are in this business at the leading edge. The design of these very sophisticated chips is costly itself. It costs about $500 million and takes a design team of about 1,000 engineers to design one of these leading edge chips. Now, the US consumes about 50% of all the chips that are produced globally, but we only manufacture about 10% of them. So we've recently learned that that's a concern and how fragile supply chains are. We continue to lead in chip design and in things like manufacturing tools for chips, but we've fallen behind in the actual manufacturing of the chips. So bottom line, making transistors smaller, which is what's driven progress for 60 years or so, is getting really, really, really hard. And yet, we all just assume that we're going to be able to do more and more with our electronics every year. And we have this appetite for more. How are we going to do that? That's the big question in my field. Well, Dennis Buss was a major figure in semiconductor technology for a long time, spent most of his career at Texas Instruments. We invited him to Purdue in 2013 when we could start to see the end of Moore's Law, and asked him, what do you think about the future? Well, Dennis thought, what we're going to see is differentiated technology is going to become more and more of an advantage. That is certainly playing out. You're seeing now companies like Apple, more and more the electronics is a differentiating factor in your products. And if you're going to differentiate your products from your competitors, you need to be designing your own chips, not using commodity chips that everybody has. So Apple designs their own microprocessors. Every automobile manufacturer has announced that they will be designing their own chips. We're going to see more and more of this kind of differentiated technology. The innovation, for years we've had Moore's Law. We know what to do. You make the transistors smaller, you double the number on the chip, you just keep doing that. Well, we don't have these long-term roadmaps anymore. We're going to have to continue to innovate, but it'll be in a variety of ways and it'll be less predictable. There are lots of problems and challenges and opportunities, and the evolution will be driven by those. And what we're really going to see is, in the beyond Moore's Law era, is a much more, even more exciting new era of innovation that is going to we're going to have to fuel progress in the coming year. So, what we're going to see in this era, there's going to be an increasing amount of custom design, but we have to learn how to make it more affordable so that more and more companies will be able to design the electronics for their own products. We can do things like exploiting the third dimension. Right now, we put transistors on the surface of a silicon chip. We can begin to stack them in vertical layers and get more transistors on the same chip. In, for example, 3D NAND memory, there are almost 200 layers of memory devices on a NAND memory chip. We will be doing more and more of systems in package. So these are sophisticated packages that can house different chips from different technology generations and different technologies, silicon and RF and power, MEMS and photonics, that can be put together in a way that you don't suffer large penalties and power and delays and going from chip to chip. So that's a very promising way to continue to fuel progress in the future. There'll be creative uses of putting different kinds of technologies together in these advanced packages. And there are lots of opportunities for the more mature. Not every application requires leading edge chips. And there are lots of opportunities for doing innovative things with chip technology that is more mature and not at the leading edge. One of the key things that we're going to be needing to do is to be thinking about new ways of processing information that is more efficient than the ways that we are doing it currently. So the ways that computer systems operate today, this so-called von Neumann architecture, is the way that was first devised by John von Neumann in the late 1940s and was the basis for the very first electronic computers. And we're still building computers with that same basic architecture of logic and memory. We have to think about new ways of doing that creatively, maybe perhaps inspired by the human brain. And we're going to see a whole new wave of innovation when we learn how to do information processing in fundamentally new ways. Now, at this point, I would like to, a slide or two, and then I'll turn the rest of the talk over to my colleague to talk about those new ways of information processing. So I think America has realized recently how foundational this technology is to our future. how fragile supply lines are, how critical it is if a nation aims to control its own destiny, that it be strong in chip design and chip manufacturing. And this is a sentiment that's shared by both houses of Congress. There's pending legislation that will be directed at incentivizing companies to reshore chip manufacturing. But we need to do more than just build more factories. Since we're approaching, Moore's law progress is continuing, but it's slowing down dramatically. We need to re-energize US microelectronics and power progress with a whole new wave of innovation. So it'll involve challenges and opportunities, and education will play an absolutely critical role in it. So with that, I will turn the remainder of the talk over to my colleague, Professor Kaushik Roy, who spends his time thinking about new ways to process information, non-traditional ways. So Kaushik. I'm sorry?
No.
I'm a little hearing challenged, so this may be...
How does Bob Noyce's invention differ from Jean Hornig? They were both at Fairchild Semiconductor, but it's Noyce as well as Kilby who have the integrated circuit.
Well,
Horney was at Fairchild with Noyce, but Noyce is better known to most people.
Yeah. All right, so if I got the gist of it, the actual first demonstration of an integrated circuit was done by Jack Kilby at Texas Instruments.
Yes.
Okay. The real technology that made it possible and that
Silicon.
was silicon with the planar process that was done at Fairchild Semiconductor.
And
yeah.
so Noyce got that important patent, and then ultimately it was shared with Kilby. Somehow Texas Instruments and Fairchild came to some agreement. And Horney was sort of a terrific guy on the side. I just wonder, you didn't mention Noyce, and I know that Noyce.
Yeah, it's. I'd be happy to discuss this with you. I don't want to take my colleagues' time. The history is fascinating. And if you look at an old Life magazine article from that time period, you'll see a picture of the 6 inventors of the integrated circuit. And over time, this came down to 2, Noyce and Kilby. But I'd be happy to talk more with you about that.
Thank you.
All right. Thanks, Mark. All right. Things are not coming out all right, but anyway, let's see if it works or not. Now imagine that right after my talk, I have my self-driving car waiting for me outside. It tackles the traffic of Phoenix, takes me to the airport. I fly home, and I always find my dogs waiting for me. They're always excited to see me. And but today I also have my personal robotic assistant, quite delighted to see me. They figure out the mood that I'm in and makes me a really strong cortado with a little bit of dark chocolate. And finally plays my favorite song, which my son, I found that they don't know about Beatles, but they play Beatles for me, which is, Hard Day's Night. When I get home to you, I find the things that you do makes me feel all right. Now this can be a reality. The C3POs and the R2-D2s that George Lucas talked about, that's not just the imagination of him anymore. That can potentially be done today. So to that effect, if I were to really look at the machine learning saga, that has made a huge amount of progress, the deep learning. What we look back in 97, I think, things are not coming out right for whatever reason. The Deep Blue beating Kasparov. And then in 2011, I think, it was actually, the Jeopardy actually was won by Watson. And with the advent of deep learning back in 2011 and so on, a lot of exciting things happened. And that was really fueled by powerful GPUs and the availability of data. And in 2016, I think, it was AlphaGo beating Lee Sedol. And finally, today it's almost impossible to beat the machine. Today the grandmasters, they actually play with really the machines. But the question, of course, is at what cost? So if I were to really look at the energy consumption, the power dissipation of these exciting systems that have been developed, they were in the range of hundreds of thousands of watts. So whereas if I were to look at the brain, that probably does it at about 20 to 30 watts of power consumption. Now, while we are making a huge amount of progress today in the area of algorithms and learning algorithms, the hardware cost is moving further and further. And interestingly enough, certainly our aspirations have grown faster than the technology is there to satisfy them. So if I go further then, and if I have to go into a little more details of how things are happening, and this is an example of where I'm showing the machine learning applications and the training cost. And I'm plotting on the y-axis in this particular case, the number of operations. And if I were to really look at some applications like, for example, image classification or for example, language processing, it turns out the number of operations required, by the way, the y-axis is in terms of zeta operations, which is 10 to the 21. So humongous number of operations required to do. I don't know how to go back now. Somehow it's just going in its own order. But anyway, turns out the number of zeta operations, which is 10 to the 21 for some of these applications, is really humongous. So now if I were to really look at, for example, correspondingly the carbon footprint of some of these benchmarks for training, as an example, the round trip flight between New York to San Francisco per passenger is about 17x lower in terms of carbon footprint than training some of these complicated AI applications. So again, that's not quite sustainable in terms of energy consumption and power consumption. Now, on the other side of it, if you were to really look at, for example, edge applications, and in particular, actually, we did an analysis of object recognition in a smart glass with state-of-the-art accelerator, and we used a Google Edge TPU. Turns out, and when we are implementing, for example, something like a RetinaNet DNN to recognize objects, turns out the battery life under ideal conditions, it's going to be of the order of about 64 minutes, which is about an hour. So now if you really consider the real situations with display taking a good amount of power consumption and so on, turns out that the battery life is probably going to be less than half an hour or so. And that, again, is also not sustainable. So the question, of course, is where do these inefficiencies come from? So the inefficiencies do come from the fact that, hey, if you want to be closer and closer to the brain, we don't really know the exact learning algorithms in our brain. We don't even know, and again, it's going in its own way of going forward. But anyway, we also don't know the hardware architecture of the brain. So if I were to really think about the hardware architecture, today's von Neumann architecture that Mark talked about, that has a memory on one side and computing on the other side. And turns out that when we want to do computation, what you have to do is you have to go to the memory, take data from the memory, go to your central processing unit, do the computations, and then bring it back to your memory again. And that's extremely inefficient. So unfortunately, I mean, the slides are going in its own way. I don't have any control at all. So you can almost ignore the slides. Sorry about it. I mean, again, going much, much further than what I've said so far. But anyway, that certainly is not the kind of architecture I want. Brain certainly doesn't have CPU on one side and a memory on the other side. It's all mixed up together, and the computations are done in a very, very interesting and a complicated way in the memory itself. Can I go back to my slides again? I mean, 2 slides back. I mean, it's almost like I can forget about this little tool that I have. One more, yeah. So, and on the other side of it, Mark talked about transistors. One of the greatest innovations. The transistors being on-off switches are excellent. And that done a fabulous job. But then again, when I try to implement, for example, neurons and synapses, they are not suitable for implementing them. Not very suitable to implement them. So now if I had to really go, think about circuits and architecture, they need to look more like neurons and synapses if I can efficiently implement some of these algorithms in a hardware architecture. Going forward, the next slide is beyond the compute demand, there are a few other things also one has to worry about. When it comes to AI, Today, AI, as I was mentioning, training, that requires a humongous amount of effort, right? It requires a huge amount of data to train things. So is it possible that I can train with less data? And probably humans can do that better. Now, on the other side of it, the question is, how well can we generalize? If I show this chair that I'm showing here, and then I learn about that to be a chair, the question is, the other ones that I'm showing at the bottom, are they chairs? So from the context of it, they're all chairs. However, would my system do that? Then finally, there's something called robustness of these systems. And again, it just vanishes in the background. But what I was showing is a macaw. And my system learns it as a macaw. But now let's say that I add a little bit of a noise to it. And it's a crafted noise. And then my macaw now all of a sudden becomes a bookcase. It has no similarities at all. So the robustness of today's AI systems is notorious. And finally, the other thing that is also important is as humans, we can keep on learning over time and we don't keep forgetting things. So the question, of course, is can I continuously learn over time? So those are very, very important issues that one has to really think about and learn. So now going forward, hopefully it's clear by now that in order to really make a difference and to be able to actually do computations with less amount of energy with a good amount, improved latency, there's a need to really think about not just the learning algorithms, but also the hardware, and at the end of it, the circuits and devices. So to that effect, going forward, now, can we take cues from the brain? At least we have an existential proof that the brain is reasonably efficient, right? So why can't we take cues from the brain and try to look at what are the things that we can really do? How about the neuron models? The neuron models that we use today, can they be simplified neuron models? Can we use, for example, the learning algorithms that the brain uses? And again, we don't have complete understanding of it. Can we use the hardware architecture, which has similarities with what the brain is? For example, there's a good amount of work that has been done in the visual cortex, in the primary visual cortex. Can I use that? And again, as I said, we're out of that slide that I'm talking about, and the network architecture of the brain. Can we mimic that? So to that effect, in order to address these problems, we're introducing, actually at Purdue, we're introducing this new institute of hard AI. And this turns out to be a really good place to introduce the Institute of Hard AI, which is HAI, which actually rhymes with NAI too, in some ways. So it turns out it's a good place to do that. So the Institute of Hard AI, where we are actually going to look at AI by hardware, AI for hard stuff, and AI for physical things. So what we mean by that, I think there's going to be a flyer outside, where we discuss the different areas of research as a part of this institute that we're going to be looking at. As I mentioned earlier, looking at the algorithm side of things, algorithms, the learning algorithms that can efficiently learn, the hardware that can efficiently implement some of these algorithms. So devices that can mimic the neurons and synapses in an effective way. Edge computing, as I mentioned earlier, there's a need for really thinking about latency. There's a need for thinking about power consumption, energy consumption in some of those hardware, because those are all going through the roof. And AI for physical things, you have to really think about the application domain. There are various things that one can look at, certainly self-driving cars, self-driving trucks, autonomous navigation, pharmaceutical manufacturing, digital agriculture, you name it, AI can potentially help. The different initiatives that at Purdue we can be looking at, and at the core of it is certainly going to be research and innovation, but we are going to be also developing the workforce. So there'll be different short courses related to hard AI for both industry and academia, different lecture series, industry partnerships, workforce development, technology commercialization. These are a few of the areas that we can be looking at. So I'm really excited to launch this institute today. And as I mentioned, it turns out in an AI conference, turns out to be an exciting place to start that initiative. Thank you.
I'm from Atlanta. great talk. You talk so much about our brain. That's fantastic. One thing about why human brain can work so well with this all this fast processing is because take advantage of calcium signaling for the network. So we should talk.
Yeah, no, that's an excellent point. I mean, a lot of times actually we don't know what brain does, but can we take some certain cues, the models of the neurons, and again also remember that I don't have the brain hardware to play with. I really have transistors and maybe other metallic devices that can communicate with electrons or maybe some other means. Yes.
Yeah, the temporal spatial change of the calcium signaling, not just control the whole body or life universal of all live organ. It's fascinating, especially at the brain, how it's organized at the dynamic talked. The unique invention from our group is we're able to develop the calcium sensors, which can capture the really fast communication between different parts of the brain. That is something perhaps you can add in your AI initiatives. Thank you.
Yeah, thank you very much, yeah.
Rich Meager, University of Georgia. So I was wondering, I was fascinated to find out several years ago that the brain used more energy per gram of tissue than any other organ in the body, except maybe an exercising muscle. Usually 10 times, 20 times more energy. Is there anything to be learned from that about either storage or processing information in terms of how you're going to design these AI systems?
Yeah, no, again, a very good point. I mean, we don't have a whole lot of understanding of it. I mean, whether it's exactly 20 watts, 30 watts, or 40 watts. We certainly know our transistors are way faster than the neurons, but there's a huge amount of parallel processing in some ways that goes on, right? Connectivity is absolutely important. In a three-dimensional way, it's very well connected. How is the memory organization done? We also don't understand it very well, but we certainly know at least the von Neumann computing techniques where we have a separate memory and a processing unit that may not be very well suited for the kind of algorithms that we're looking at. So the question is that there's still a long, long way to go. We just, not even the tip of the iceberg. But the question, of course, is that can I solve today's problems in a little more efficient way than what we are doing, able to do today?
I'd like to talk to you more after the session.
Sure. Okay. Thanks.
Thank you to Kaushik and Mark for that very interesting presentation. James Conley from Northwestern University, by the way. It occurred to me as you talked about training sets and the inability to see how the human mind works. Maybe there's one that already exists that is secondary from actual, neural processing, but it is an explicit record. It includes 180 million documents across the history of time that it is the actual patent disclosure database. So from the point of view of technological innovation and how the mind has worked in that sense, I wonder if that could not be your training set.
Again, these are all very, very important, difficult, and interesting questions. And, to tell you the truth, as I said today, a lot of things that we're doing, I think we're doing sort of in a dumb fashion, if I may say so. We dump it a huge amount of data, and then, hey, let it train in some interesting ways. So the question is, can I really train in an effective way? And in fact, maybe the human brain comes wired in some ways when we are born, to a certain extent. Again, we don't know these things, but how do you train with less data? What would be a good training site to train on? Those are all very, very important questions, but I don't have an answer to it. Hopefully, from the point of view of applications that we're looking at, can I do a better job?
The economists who we typically don't interact with have been addressing this problem with vector analysis, word vector analysis. So let's chat after the meeting.
Sure.
Thank you again, Kaushik and Mark.
Thanks.
I think this is a really important question. The key is what is a ground truth in this related field? Jim just raised a great point, but requires people in the audience here coming together to work on this very interactive true problem. to
Right.
s-
No, again, these are all very interesting questions, and I must also admit, it's all something that we're not trying to emulate the brain, and we can't, at least from what we understand, what we know. The question is, for a class of these problems that we have, could be a recognition problem, could be understanding, scene understanding, could be able to autonomously fly with, let's say, vision sensors without any GPS, as an example, where you need to do optical flow, depth estimation, object avoidance and dodging. Can I do that in a little more effective way, much more effective way, more energy efficient way, by, even though I may not understand the brain, but there are little things that that I may help in making this problem, to have this, to come up with a better solution, so to say.
Right.
And not quite really trying to mimic the brain at all.
Yeah, this is King Lee here, and a doctor and also bioengineer from UIUC. I think, well, you have to look this way on this side.
Oh, I'm sorry.
Yes, yes.
It's too much light.
Yes, I think we have been ignoring the complexity of how the brain works, right? We talk about, ion channels and so on. Those are the fast part of the brain processing. In fact, the brain has a much longer lasting part that is very little understood. And that's the epigenetic part of the control of the brain, right? For example, if you put a finger in a fire, you remember it forever, right? I mean, how does it work? Versus, right, you taste some good food, you may forget it. There's a lot of experiences that we have, we forget quickly. And some will last forever. How does that screening work? And how do you record that, right? And that's actually the epigenetic part of the brain. You're born with a personality. We know that, right? When we now understood that it's actually through epigenetic encoding, right? How does the epigenetic encoding work with the fast part of the brain to allow us, right, to do all the things that we do is fully understood. How did that circuit work, right? That you actually go into the epigenetic molecular encoding that can work with the fast ion channels to make our brain function that it is. It's very different from your transistors. It's very different from the memory that you bring in. It's very different from the software you use to encode, right? So those are all particular things that you need to really fully understand to even emulate the first layer of how the brain works.
These are very, very important questions. We are not talking about it from a neuroscience point of view. This institute is really more application driven. I mean, if you really think about it, right? A lot of things, a lot of problems are being solved today, in maybe not a very efficient way, using neural networks. You might say, hey, our neural networks very, very weakly inspired by the brain, very weakly inspired. But the question, of course, is, from our point of view, are we able to solve a class of problems more effectively using a hardware architecture, right? That today we have available to us, or maybe we can look at, for example, devices that can more, are better suited for these applications, as opposed to, no, I don't have the neurons, I don't have the synapses, we don't even understand a lot of things, but hey, can I really, look at these applications, look at a different kind of architecture where it's non-von Neumann-like, where the computations can potentially be done a little bit in the memory itself, in an effective way, to be able to get an energy efficiency, which is hopefully 100x, 1000x better
Absolutely.
than what
That's
we can do
what
today.
I'm thinking about, right? So instead of thinking about using current architecture, can you think about emulating the brain using different layers of architecture, right? The epigenetic organization is totally different than the fast ion channel organization. But they can work together, right? To make things a lot more efficient and have different layers of problem solving, right? Which is not figured in our current thinking of computer architecture or computer software writing, right? So if you really want to push the limit of that, you need to get outside of the box of current architecture and software development and embrace something totally outside of the box.
You're absolutely right. Today, the standard is the von Neumann architecture.
Right.
And in fact, the non-von Neumann, by the way, is a big leap from what we're doing, what's done today. Computing in memory, by the way, would require analog processing as an example. I'm just taking small steps. I'm not talking about,
Right, so you
really
have to think
mimicking
about
the brain. Just to
right?
put things in perspective. I'm not trying to mimic.
So it
the brain.
certainly appears we have landed on a topic of great interest to all of our audience, and I think one which can easily lead over to the break.
Thank you. Thank you.
Thank you.